Hi everyone. Today we'll learn what it means for a function to be concave up, to be concave down, and what inflection points are. In the first exercise, we're given three functions, and we must determine if these functions are above or below all of their tangent lines. If you would like to try this exercise on your own first, stop the video now. You can download these notes using the link in the video description. In the first example, no matter where I draw a tangent line, that tangent line will be below the graph of the function. The graph will be above the tangent line. Let me show you. If I draw a tangent line right here, this is how the tangent line will look like. It is below the graph of the function. The graph of the function is above that tangent line. If I draw a different tangent line, the same thing will happen. The tangent line is below the graph of the function, which means that the function is above all of its tangent lines. Same thing in the second example. No matter where I choose to draw a tangent line, that tangent line will be below the graph of the function. The graph of the function will be above the tangent line. Same in the third example. If I draw a tangent line, the graph of the function will be above the tangent line. This is not always the case. Take a look at the next three examples. No matter where I draw a tangent line here, that tangent line will always be above the graph of the function, which means that the graph of the function will be below all of its tangent lines. Same in the second example, the middle example. No matter which point I choose, if I draw a tangent line there, that tangent line will be above the graph of the function. The graph of the function will be below the tangent line. Similarly, in the last example, no matter where you draw the tangent line, the graph will be below the tangent line. The graphs that are above all of the tangent lines, like the first three we saw, are called concave up. The graphs that are below all of their tangent lines are called concave down. A graph that is concave up curves up away from the tangent line. A graph that is concave down curves down away from the tangent line. People mostly think about concave up functions as those that resemble smiley face or a piece of a smiley face. You can think about this graph as a smiley face, this graph as a piece of a smiley face, and this graph as a piece of a smiley face. When it comes to concave down functions, they look like sad faces or pieces of sad faces. Again, to be concave up means that the graph lies above all of its tangent lines. To be concave down means that the graph lies below all of its tangent lines on an interval. Let's see if we understand this definition by looking at the graph of a function and determining where this function is concave up and where this function is concave down. If you would like to try this exercise on your own first, stop the video now. I believe that at first the function is concave up. It resembles a smiley face. No matter where I draw a tangent line, the graph will be above the tangent line. The graph will curve away up from the tangent line. And I have a graph that is concave up, concave up, concave up, and somewhere here it changes and it becomes concave down. So I will say that this graph is concave up from negative infinity to, let's say, negative 2.5. Then at 2.5, it becomes concave down all the way to this point, where at this point it changes into a concave up function again. So it goes from negative 2.5 to 0 is where the function is concave down. Then we say that the function is concave up. It looks like a smiley face between 0 and 2. And then again, the function is concave up. Again, I have a smiley face. If I was going to draw a tangent line anywhere, the graph would be above that tangent line. So I have a function being concave up between 2 and infinity. There are places on this graph where this function changes from concave up to concave down and vice versa. I believe there is a point right there where the function changed from being concave up to concave down. There is a point right here where the function changed from being concave down to concave up. Note that here the function did not change from concave up to concave down. Over here the function remained concave up. It was concave up and then it was concave up again. Places where the function changes from concave up to concave down and vice versa are called inflection points. An inflection point has two coordinates, and we call that point an inflection point if the function is continuous there and the graph changes concavity there from concave up to concave down or vice versa. Let's see if we understand this definition by trying to identify all the inflection points of the following function. If you would like to try this problem on your own first, stop the video now. I believe there are a few places where this function changes from concave up to concave down and vice versa. At first, this function is concave up, and somewhere here it changes to concave down. I believe this point happens at x equal to -3. So this inflection point has the x coordinate -3, and it also has the y coordinate of -2. Remember, inflection points always have two coordinates, the x coordinate and the y coordinate. Then the function is concave down, concave down, concave down, and then it again is concave down, which means there is no inflection point at -1. And the function is concave down, and then it becomes concave up again, which means there is a point right here where the function changes concavity, which means there is another inflection point. That inflection point has x coordinate equal to 1, y coordinate equal to -2.